December 20th, 1943, RAF Bassingbourn, England. The air raid sirens weren't wailing. No German bombers prowled the gray English sky. But the crash crews were scrambling anyway, racing toward the runway where something was about to happen that would either be a miracle or a massacre. Lucky Strike was coming home, or what was left of her. Control tower operators watched through binoculars as the B-17 dragged itself across the English Channel like a wounded animal that refused to die. The No. 3 engine wasn't just dead, it was gone, torn off by flak over Bremen, leaving a gaping wound in the wing where 1,200 horsepower used to live. Hydraulic fluid painted red streaks along the fuselage as if the bomber were bleeding. The ball turret hung at a sickening angle. By every manual, every regulation, every physics calculation the Army Air Forces had published, this bomber should have augured into the North Sea 20 minutes ago. But Lieutenant Marcus Webb kept that crippled bird airborne through a combination of brute force, prayer, and something else. Something the ground crew had done to his plane 3 weeks earlier that wasn't in any manual, wasn't in any technical order, wasn't supposed to exist at all. Webb called the tower. His voice was steady, but you could hear the exhaustion underneath. Bassingbourn Tower, Lucky Strike. Coming in hot. Hydraulics are gone. Landing gear, working on it. The tower controller's stomach dropped. No hydraulics meant no landing gear, and a B-17 doing a belly landing was often a B-17 that caught fire. Webb fought that airplane all the way to the threshold. When the wheels finally came down, only one of them, the other having refused to deploy because technically there was no hydraulic pressure left to deploy it, everyone watching held their breath. Lucky Strike kissed the runway on one landing gear leg and skidded down the tarmac in a shower of sparks that could be seen from a mile away. The shriek of metal on concrete was like nothing the crash crews had heard before. The Fortress spun, slewed, and finally ground to a smoking halt at the end of the runway. The crash crews expected to pull out bodies. Instead, they found 8 men climbing out on their own power, shaken, exhausted, alive. The 9th man, the ball turret gunner, had been lost over the target, but everyone else made it home despite flying a plane that had, according to post-flight analysis, lost primary hydraulic function, suffered catastrophic fuel system damage, and experienced electrical failures that should have made controlled flight impossible. Group Commander Colonel James Albertson stood on that tarmac, staring at the wreckage. Engineers were already swarming the aircraft, trying to understand what they were looking at. Albertson asked the only question that mattered: how? The official answer would take months of investigation, engineering analysis, and bureaucratic hand-wringing. The real answer was already working in a hangar 200 yards away, elbow deep in another B-17's engine cowling, making modifications that would get him court-martialed if anyone had bothered to document what he was actually doing. See, the Army Air Forces in late 1943 had a problem they couldn't quite articulate in the after-action reports. Bombers were going down. That was expected. This was war over Nazi Germany, after all, and the Luftwaffe wasn't handing out participation trophies. But planes were going down from damage that shouldn't have been fatal. A single flak hit in the wrong spot, and a B-17 that could supposedly absorb punishment that would shred 3 fighters would just fall out of formation. Controls would lock up, engines would sputter and die, electrical systems would fail in cascading waves. Something was wrong with the design, but Boeing wasn't about to admit it. The Pentagon wasn't interested in hearing it, and crews were dying because of it. Lucky Strike's survival wasn't luck. It was proof that someone had figured out the flaw and fixed it, using methods that would make procurement officers have aneurysms and generals reach for their court-martial paperwork. This is the story of how one mechanic's forbidden modifications turned the B-17 from a statistical death sentence on certain missions into the legendary survivor it's remembered as today. And it started with a guy who'd learned to fix things not in any technical school, but in a Depression-era garage in Pittsburgh, where the rule was simple: make it work, or it doesn't get fixed. Staff Sergeant Paul Zuk wasn't supposed to be fixing airplanes. His Army Air Forces personnel file said he'd scored high enough on mechanical aptitude tests to warrant assignment to the motor pool, trucks, jeeps, the unglamorous machinery that kept an airbase running but never got within 100 yards of a runway. But someone in the assignment office at Bassingbourn had looked at his civilian work history and made a lateral move that probably saved 100 lives. Before the war, Zuk had run a repair shop in Pittsburgh's Polish Hill neighborhood. Not the kind of shop that catered to wealthy clients with new Packards. The kind where you fixed coal trucks, delivery vans, and the occasional bootlegger's souped-up Ford on budgets that would make a poverty line look generous. Polish Hill in the 1930s didn't have the luxury of waiting for factory parts or calling the manufacturer when something broke. You fixed it with what you had, or it didn't get fixed. Period. Zuk learned to look at a broken fuel pump and see not what it was supposed to be, but what it could be made to do with a length of rubber hose, some baling wire, and the kind of ingenuity that comes from necessity being the only mother of invention you've got. He arrived at Bassingbourn in August 1943. 26 years old, grease already under his fingernails, an attitude about regulations that his commanding officers would alternately find infuriating and invaluable. His first week on the flight line, he watched a crew chief reject a B-17 for a cracked hydraulic line. Standard procedure, by the book, completely correct according to Technical Order 01-20EG2. The replacement part was on back order. The plane sat grounded. The mission went out one bomber short. Zuk asked why they couldn't bypass the damaged section and reroute through the secondary line. The crew chief looked at him like he'd suggested using baling wire to fix the wings. "That's not in the manual, Sergeant." Zuk's response, delivered in the Pittsburgh accent thick enough to cut with a wrench, became legendary in the maintenance section. "The manual didn't grow up fixing trucks during the Depression. I did." Here's what made Zuk different from the mechanics who learned their trade in Army technical schools. Those guys could follow a technical order perfectly, execute repairs exactly as Boeing engineers had specified, maintain a B-17 to factory specifications. Zuk could look at a system that was failing and ask the question the engineers apparently hadn't. What happens when this breaks over Germany and there's no parts depot at 20,000 feet? His genius wasn't in understanding how things were supposed to work. It was in understanding how they could still work when everything went wrong. By October, other mechanics had started noticing something odd. Planes Zuk serviced had a weird habit of coming back from missions they shouldn't have survived. A bomber he'd worked on took flak through the hydraulic bay. Should have lost all landing gear control, but the pilot managed a wheels-down landing. Another bird lost primary electrical after a fighter attack, yet the instruments kept working long enough to get the navigator home. Coincidence. Lucky coincidence. Zuk didn't believe in luck. He believed in redundancy, in backup systems, in routing critical functions through pathways that weren't in the Boeing blueprints because Boeing had apparently never considered what happened when their beautiful, efficient, single point of failure designs met German 88mm flak. While other mechanics replaced parts, Zuk was redesigning systems on the fly, using scavenged components, borrowed tubing, electrical connections that would have made an inspector weep. The other mechanics started calling him the plumber because he was always rerouting something. Hydraulic lines, fuel feeds, electrical bundles. He'd spend hours after official duty hours in the hangars, flashlight clenched in his teeth, rewiring planes in ways that never appeared on the maintenance logs, because technically, what he was doing violated about 15 different Army regulations. When asked why he bothered, given that he could have sat in the motor pool drinking coffee and avoiding trouble, Zuk's answer was simple. Those guys fly the missions. Least I can do is make sure the plane doesn't kill them on the way home.
The B-17 Flying Fortress was supposed to be indestructible.
Boeing's marketing practically said so, and the early combat reports from 1942 seemed to confirm it. Fortresses came back from missions looking like flying cheese grayers. Holes punched through wings and fuselage, tail sections shot to ribbons, cockpits shattered. Yet they kept flying. Crews nicknamed them the Flying Fortress for good reason. These things could absorb punishment that would atomize a B-24. Hell, there were stories of B-17s landing with entire tail sections blown off, with engines torn from their mounts, with wings that looked like Swiss cheese. But by late 1943, a disturbing pattern emerged in the lost statistics. A pattern nobody wanted to talk about, because talking about it meant admitting something uncomfortable. Planes weren't just getting shot down by concentrated fighter attacks or direct flak hits to critical areas. They were going down from single points of failure. One hit in the wrong spot,
and a bomber worth $200,000 and 10 trained airmen would spiral out of formation and disappear into the clouds below. No fire, no explosion, just gone. The 8th Air Force was losing bombers at a rate of about 5% per mission by autumn 1943. Do the math on that. A crew's odds of surviving a required 25-mission tour were essentially a coin flip. 50-50 that you'd make it home or end up as another name on the missing in action lists that got longer every week. Something was killing B-17s that shouldn't have been fatal. And it took mechanics like Zuk, guys who actually looked at the wreckage when it limped home, who crawled through the twisted metal and tried to understand why systems failed, to figure out what the problem was. Hydraulics. The B-17's hydraulic system controlled everything that mattered when you were trying not to die. Landing gear, brakes, wing flaps, and most critically, the turret systems that let gunners track fighters trying to kill you. Boeing had designed an efficient system, primary lines running through the fuselage in tidy bundles, because that's what you do when you're designing for peacetime efficiency at assembly line production. But efficient meant concentrated. One piece of flak through the wrong 6 inches of fuselage, and you lost hydraulic pressure to multiple systems simultaneously. A bomber could have 3 functioning engines, intact wings, a healthy crew, but without hydraulics, you couldn't lower landing gear. And a B-17 doing a belly landing on an English runway was often a B-17 that caught fire when metal scraped on concrete and ignited leaking fuel. Then there was the fuel system, which had its own special way of killing people. The B-17 carried 2,780 gallons of high-octane aviation fuel in 9 different tanks, 5 in the wings, 4 in the fuselage. The feed system was designed so fuel flowed from outer wing tanks inward, maintaining balance as you burned through your load. Sensible engineering, textbook design, except the fuel lines between tanks ran in areas that were absolutely in the cone of fire when German fighters made beam attacks from 3 o'clock or 9 o'clock positions. A 20mm cannon round through a fuel line didn't just mean you lost fuel, though you did catastrophically. It meant you now had aviation gas spraying inside an airframe where hot metal, electrical sparks, and open air at minus 40 degrees created perfect conditions for either fire or vapor lock. Zuk had noticed something the engineering reports missed. Planes that went down from mysterious causes often showed pre-impact fuel system anomalies. Pilots would report rough engines, then engine failure, then the whole plane would shake itself apart or catch fire. Post-crash analysis, when there was anything left to analyze, kept mentioning fuel contamination or air in the lines. What was happening was simple once you saw it. Flak or bullets would damage a fuel line, air would get into the system, engines would start dying in sequence because they were all fed from the same compromised network, and the bomber would go down not because it was too damaged to fly, but because it was choking itself to death. Boeing's engineers had built an airplane that worked beautifully under ideal conditions, but combat over Germany in 1943 wasn't ideal conditions. It was an environment where every system needed to assume it would be damaged and still had to work anyway. The B-17's Achilles heel wasn't armor or firepower. It was single point of failure design philosophy. And that's what Zuk started fixing. One unauthorized modification at a time. What Zuk did wasn't technically illegal. It was worse than that. It was unauthorized field modification of combat aircraft systems, which meant if a plane crashed and investigators traced the failure to his handiwork, he'd be facing a court-martial for negligent homicide. But Zuk had done the math differently. If he did nothing, the planes crashed anyway. At least this way, they had a chance. The core of his forbidden fix was brutally simple. Create redundancy where Boeing hadn't. Take that hydraulic system with its neat, efficient single-bundle design and turn it into a mess of backup lines that looked like a plumber's nightmare but functioned when the primary system took a hit. Zuk started scavenging hydraulic tubing from damaged aircraft in the salvage yard, stuff that was technically supposed to be sent back for official recycling. He'd cut sections of undamaged line, test them for pressure integrity using a hand pump he'd jerry-rigged, and then install them as bypass routes in active aircraft.
Here's how it worked in practice. A standard B-17 had one main hydraulic line running from the pump to the landing gear actuators. Zuk would tap into that line at 2 points, one forward near the cockpit, one aft near the radio room, and run a secondary line along a different path, usually tucked along the fuselage stringers where it was protected by structural members. Then he'd install manual isolation valves at each junction point, using parts cannibalized from damaged bombers. If the primary line took a hit and lost pressure, the pilot could reach down. Zuk mounted the valves within arm's reach and manually switched to the backup line. It wasn't elegant. It added weight. It violated Technical Order 01-20EG-2, Section 4, Paragraph 12, Subsection C. And it meant the difference between landing on wheels or sliding down the runway on your belly and praying. The fuel system fix was even radical. Zuk couldn't prevent fuel lines from getting hit. That was a fact of flying through flak. But he could prevent a hit from cascading into complete system failure. He started installing crossover valves between tank systems, using fuel petcocks designed for ground refueling operations. Officially, these valves were only supposed to be used on the ground. Zuk installed them in flight-accessible positions and documented them on maintenance forms as refueling system check valves. Technically true, deliberately vague. Now when a fuel line took damage, pilots could isolate the compromised tank and reroute fuel flow from intact tanks directly to the engines that needed it. But the modification that really saved lives involved the electrical system. B-17s had a primary electrical bus that powered everything from instruments to turret motors. One hit to that bus and you were flying dark. No instruments, no radio, no turrets. Zuk started running secondary power lines from the auxiliary generator directly to critical systems, bypassing the main bus entirely. He'd hide these lines inside existing cable bundles so they looked like factory wiring until you actually traced where they went. He used a different color of insulation, yellow instead of the standard black, so pilots would know which breakers controlled the emergency backup systems. The brilliance of Zuk's approach was that he wasn't inventing new technology. Everything he used was already on the aircraft or in the parts bins. He was just rearranging the puzzle pieces in ways Boeing's engineers hadn't considered, because they'd been optimizing for manufacturing efficiency, not combat survivability. A bomber coming off the Seattle production line in 1943 was built to be assembled quickly by workers who'd been housewives 6 months earlier. Every system was designed for easy installation by semi-skilled labor. Zuk's modifications required a skilled mechanic who understood systems theory and wasn't afraid to deviate from the blueprint when the blueprint was getting people killed.
By January 1944, Zuk had quietly modified 17 B-17s in the 351st Bomb Group. He never advertised it, never wrote it up, just did the work during night maintenance shifts when fewer officers were around to ask uncomfortable questions. And those 17 bombers were coming home from missions at a rate that was starting to look statistically impossible. February 8, 1944. Captain Ronald Fletcher, engineering officer for the 351st Bomb Group, was having a very bad morning that was about to get worse. He had been doing routine maintenance inspections, the kind where you randomly pull aircraft from the flight line and verify they match their technical documentation, when he opened the hydraulic access panel on a B-17 called Devil's Daughter and found plumbing that absolutely should not exist. Fletcher wasn't stupid. He'd been an aeronautical engineering student at MIT before the war. He could read a blueprint. What he was looking at wasn't on any Boeing blueprint he'd ever seen. Secondary hydraulic lines running through non-standard routes, manual isolation valves installed in locations that required custom bracketry, fuel crossover connections using parts from what appeared to be 3 different aircraft. And all of it done with the level of craftsmanship that suggested this wasn't some sloppy field expedient. This was deliberate, thought out, modified. He found Zuk in Hangar 3, working on an engine swap. "Sergeant, we need to talk about Devil's Daughter's hydraulic system." Zuk didn't even look up from the cowling he was torquing. "What about it?" Fletcher pulled out his inspection clipboard.
What about the fact that there are approximately 40 feet of unauthorized hydraulic line installed in non-standard routing with manually operated valves that aren't in the technical orders? Zuk set down his wrench, wiped his hands on a rag that was somehow dirtier than his hands, and gave Fletcher a look that was equal parts tired and defiant. You want the official answer or the real one? Fletcher's response was immediate. Both, starting with how long you've been doing this and how many aircraft are affected. 17 planes. That was the number that made Fletcher's blood pressure spike. 17 aircraft in active service with undocumented modifications to primary flight systems. The regulatory violation was staggering. Zuk could be court-martialed. Fletcher himself could face disciplinary action for not catching it sooner. But then Fletcher asked the question that changed everything. Have any of these 17 aircraft experienced hydraulic failure? Zuk pulled out a grease-stained notebook from his coverall pocket, his personal maintenance log that wasn't part of any official record. 3 of them took flak hits to primary hydraulic lines. All 3 made it home on the backup system. Lucky Strike landed on her own gear 2 weeks ago after 88mm took out her primary line over Frankfurt. Pilot didn't even know he was on backup until I showed him the damage post-flight. Fletcher did the math in his head. 3 catastrophic hydraulic hits. 0 losses. The standard statistics said at least 2 of those planes should have been written off. By noon, Fletcher had escalated to Group Commander Albertson, the same colonel who'd watched Lucky Strike's miraculous landing back in December. By 1400 hours, Albertson was in the hangar, personally inspecting Zuk's modifications, with Fletcher providing technical narration. And by 1600 hours, there was a very uncomfortable meeting happening in the group operations office, where the question on the table was whether to court-martial Zuk or give him a medal. Major Henry Watkins from 8th Air Force Engineering Staff arrived on February 10th to conduct a formal investigation.
He spent 3 days crawling through Zuk's modified aircraft, photographing installations, reviewing maintenance logs, interviewing pilots. His preliminary report, filed February 13th, contained a paragraph that probably took him an hour to write, because it essentially admitted the Army Air Forces had been sending crews into combat with preventably vulnerable aircraft. While SSGT Zuk's modifications are unauthorized and violate standing technical orders, preliminary analysis suggests these changes address systemic vulnerabilities in hydraulic and fuel system design that may contribute to combat losses. Recommend against punitive action pending engineering evaluation and controlled testing. That paragraph saved Zuk's career, but it also opened a door nobody in the Pentagon wanted opened. The door that led to questions about how many crews had died because Boeing's design prioritized production efficiency over combat survivability. Albertson made a command decision that probably bent a few regulations itself. Zuk wouldn't face charges, but he also couldn't modify any more aircraft until the engineering evaluation was complete. And in the meantime, those 17 bombers would keep flying missions, because even the brass could read survival statistics. Major Watkins returned to Bassingbourn on March 3, 1944, with 2 Boeing engineers, a team of Army Air Forces technical specialists, and a mandate that essentially read, "Prove this works, or prove it's dangerous, but do it fast because we're bleeding bombers over Germany." What followed was the most informal, high-stakes engineering validation in military aviation history. Testing unauthorized field modifications under actual combat conditions while trying to figure out if you should be documenting this as innovation or evidence for a court-martial. The engineers, both civilians under military contract, were appalled at first sight. The lead engineer, a man named Carlson, who'd worked on the original B-17 design in Seattle, spent his first hour at Bassingbourn using words like contamination risk and pressure regulation concerns and potential catastrophic failure modes. He stood in front of a partially disassembled bomber, pointing at Zuk's bypass lines, explaining to Watkins why this couldn't possibly work, because it violated fundamental hydraulic system design principles established by people with engineering degrees. Zuk, standing there in grease-stained coveralls, let him finish, then asked a question.
"When's the last time you flew a combat mission?" Carlson bristled. "I'm an engineer, not a pilot." Zuk nodded. "Right, so you designed this system in Seattle, where the worst thing that happens is a failed pressure test. I maintain these birds when they come back with holes in them. Different perspective." What Watkins proposed was radical. Instrument some of Zuk's modified B-17s with additional pressure gauges, flow meters, and monitoring equipment, then send them on actual combat missions while recording system performance. In any sane procurement process, this would take months of ground testing first. But this was March 1944. The air war over Germany was hitting its crescendo. The 8th Air Force was losing an average of 6 bombers per mission. They didn't have months. Between March 5th and March 18th, 5 of Zuk's modified B-17s flew a total of 11 combat missions to targets including Berlin, Brunswick, and Friedrichshafen. Each aircraft carried additional instrumentation that recorded pressure gauges, flow rates, and system performance throughout the mission. 3 of those bombers took battle damage. All 5 came home. The data was irrefutable. On the mission to Friedrichshafen on March 18, 1944, a bomber called Memphis Belle II, one of Zuk's modified aircraft, took an 88mm flak burst that shredded the primary hydraulic line exactly where Boeing's design had it running along the bomb bay. The instrumentation recorded primary system pressure dropping to 0 in 4.2 seconds. Standard procedure, the aircraft should have been unable to control landing gear, flaps, or brakes. But Memphis Belle II's pilot, following briefing instructions Zuk had personally given him, reached down and rotated 3 manual isolation valves. The backup system kicked in. Pressure stabilized at 85% of normal, lower than ideal but well within operational range. The bomber stayed in formation, completed its bomb run, and landed at Bassingbourn on its own gear while engineers on the ground watched their monitoring equipment and realized they were seeing something that shouldn't exist, a hydraulic system that survived catastrophic failure. Carlson, the Boeing engineer, watched the data playback in stunned silence. Finally, he turned to Watkins and said something that probably hurt to admit. "This shouldn't work. The pressure dynamics are all wrong. The flow rates are inadequate. There's no proper filtration in the bypass system. But it does work. I don't understand why, but it works." Zuk, standing in the back of the briefing room, offered an explanation that probably didn't make it into the official report. "It works because I designed it to work when everything's already gone to hell. Your system works great until it doesn't. Mine works badly all the time, but it keeps working." The testing phase produced 47 pages of technical data, 11 mission after-action reports, and a conclusion that Air Force engineering couldn't ignore. Zuk's modifications increased system survivability without compromising primary system function. Translation, he'd made the planes safer without making them worse. On March 22nd, Watkins filed his final report with a recommendation that would ripple through every B-17 squadron in England. Authorize field modification based on Zuk's design, begin training mechanics across all 8th Air Force groups. April 1944. While the Pentagon argued about official procurement channels and Boeing negotiated retrofit contracts that wouldn't materialize until June at the earliest, something else was happening on airfields across East Anglia. Mechanics were talking to each other. And when mechanics talk, they don't discuss policy. They discuss what works. Staff Sergeant Mike Delacroix from the 303rd Bomb Group at Molesworth heard about Zuk's modifications through a crew chief who transferred from Bassingbourn. By April 8th, Delacroix was at Bassingbourn during a supply run, notebook in hand asking Zuk to walk him through the hydraulic bypass installation. Zuk spent 3 hours showing him every connection point, every valve placement, every routing decision. Delacroix went back to Molesworth and started modifying aircraft that night. Within a week, the 303rd Bomb Group had 5 bombers running Zuk's system. Technical Sergeant James Wu at Thorpe Abbotts heard about it from Delacroix. By April 15th, the 100th Bomb Group, the Bloody 100th, which had the worst loss rate in the 8th Air Force, had mechanics working double shifts to install bypass systems on every operational aircraft. They didn't wait for authorization, didn't file modification requests. They just did it.
because they'd watched too many bombers go down from damage that should have been survivable. This was grassroots engineering revolution spreading through informal networks while official channels debated committee structures. Master Sergeant Robert Chan at Kimballton started keeping statistics that the Air Force wasn't tracking yet. In March, before any modifications, the 379th Bomb Group had a 14% abort rate from mechanical failures during missions. By late April, with 12 aircraft running Zuk's modifications, that rate dropped to 6%. Chen's logbook, unofficial, unrecognized, showed something even more striking. Modified aircraft that took battle damage were 3 times more likely to return to base than unmodified birds taking similar damage.
The official authorization came through on April 28, 1944 as Technical Order 01-20 EG-2-127, Field Modification for Enhanced Hydraulic System Redundancy in B-17F and B-17G aircraft. It was 6 pages of bureaucratic language that essentially said mechanics could now legally do what dozens of them were already doing. But the technical order was cautious. Limited. It authorized the hydraulic modifications but made no mention of Zuk's fuel system crossovers or electrical bypasses because Boeing was still insisting those were unnecessary and potentially dangerous. Zuk read the technical order and laughed. Not a happy laugh, the bitter laugh of a man who'd watched bureaucracy almost court-martial him for saving lives and was now watching that same bureaucracy take credit while implementing only half the fix. He went back to installing fuel crossovers on the night shift, unauthorized as ever, because the paper from headquarters didn't change the fact that B-17s were still going down from fuel system failures. By May 1944, the modification had spread to an estimated 120 aircraft across 7 different bomb groups. The official number, aircraft modified under the new technical order, was 41. That gap between official and actual represented mechanics who looked at the regulations, looked at the planes, and made the same choice Zuk had made. Better to beg forgiveness than ask permission when lives were on the line. The survival statistics started showing up in ways the Air Force couldn't ignore. The 351st Bomb Group, Zuk's home unit where nearly every operational B-17 now had the full suite of modifications, including the unauthorized fuel and electrical work, had a loss rate of 2.1% in May 1944. The 8th Air Force average was 3.8%. That might not sound like much, but across a month of operations involving thousands of bomber sorties, it translated to dozens of crews that came home instead of being written off as missing in action. Colonel Albertson, in a moment of either brilliance or career suicide, invited the 8th Air Force Statistical Analysis Team to Bassingbourn in early June to review the group's survival data. He showed them everything, the official modifications, the unofficial ones, and the numbers. The analysis team's report, filed June 9th, contained a sentence that validated what every mechanic on the flight line already knew. Statistical correlation between modified aircraft and improved survivability is significant beyond normal variance and warrants expanded implementation. The revolution had become policy. Zuk had become a template. And across England, mechanics were still doing unauthorized modifications after hours because the official policy hadn't caught up to the complete fix yet. They were all Zuk now. Every sergeant with a wrench who looked at a regulation and decided that bringing crews home mattered more than following the manual. August 1945. The war in Europe had been over for 3 months when a statistician at Air Force headquarters named Dorothy Henshaw compiled a report that would never be widely published. But it told the story in numbers that couldn't be argued with. She'd taken mission data from every B-17 group in the 8th Air Force, cross-referenced it with maintenance logs documenting which aircraft had received Zuk's modifications, both the official and the unofficial ones that mechanics had carefully logged after the fact, and she'd run correlation analyses that would have made her statistics professors proud. Groups with 75% or higher adoption of the full modification package, hydraulic, fuel, and electrical, showed a 23.4% improvement in aircraft return rates compared to their pre-modification baseline. That number represented 347 bombers that made it home instead of going down over Germany or the North Sea. Multiply by 10 crew members per aircraft. Factor in that some crews survived even when aircraft were lost. And Zuk's forbidden fix had kept somewhere between 3,000 and 4,000 airmen alive who would have otherwise been killed, captured, or missing. But the number that really mattered was buried in Henshaw's appendix data. Aircraft with the complete Zuk modification package that sustained Category 3 damage, defined as damage requiring major repair or system replacement, returned to base 81% of the time. Unmodified aircraft with identical damage levels returned 47% of the time. The modification hadn't made B-17s invulnerable, but it had turned survivable damage into actual survival instead of statistical loss. Paul Zuk mustered out of the Army Air Forces in November 1945 with the rank of Technical Sergeant, an Army Commendation Medal for exceptional technical proficiency in aircraft maintenance, and no mention anywhere in his official record of the field modifications that had defined his contribution to the war. He went back to Pittsburgh, reopened his repair shop on Polish Hill, spent the next 30 years fixing cars, trucks, and the occasional airplane owned by a local flying club. He never talked much about the war. In 1973, a researcher named Dr. Michael Torres from the Air Force Historical Research Agency tracked Zuk down while working on a study of wartime field modifications. Torres spent 3 days in Pittsburgh interviewing Zuk and reviewing the personal maintenance logs Zuk had kept, the grease-stained notebooks that had never made it into official records. Torres asked the question that probably should have been asked 30 years earlier. Why had Zuk risked court-martial to make unauthorized modifications? Zuk's answer, recorded in Torres's interview notes, was characteristically blunt. "Didn't seem that risky to me. Guys were dying because the planes weren't built right. I could fix that, or I could follow the manual. Seemed like an easy choice." Lucky Strike, the bomber that started everything in December 1943, survived the war and was eventually scrapped in 1954. But photographs of its hydraulic bay, taken during the 1944 engineering evaluation, ended up in Air Force maintenance training manuals used into the 1960s. The captions never mentioned Zuk by name, referring only to field-developed redundancy modifications. Generations of aircraft mechanics learned from his work without ever knowing who done it. Boeing eventually incorporated elements of Zuk's modifications into the B-17G production run starting in late 1944, though the official documentation credited the changes to ongoing engineering refinement, rather than acknowledging they were adopting field fixes developed by a sergeant with a high school education who'd learned engineering by keeping Depression-era trucks running. The post-war B-29 and B-50 bomber programs included redundant hydraulic and fuel systems as baseline design features, lessons learned in blood over Germany and applied by engineers who'd reviewed the wartime modification data. Paul Zuk died in 1989 at age 72. His obituary in the Pittsburgh Post-Gazette made no mention of B-17s or the war, noting only that he was a veteran and had run Zuk's auto repair for 4 decades. His personal maintenance logs, the unofficial record of every aircraft he'd modified, were donated to the Air Force Museum in Dayton after his death.
They sit in the research archives now, available to anyone who requests them. 47 notebooks filled with technical sketches, pressure calculations done in the margins, annotations in a mechanic's shorthand that tells the real story of how one man's refusal to follow the manual changed the odds for thousands of airmen who never knew his name. There's a lesson in Zuk's story that extends far beyond World War II or even aviation. Sometimes, the people closest to the problem see solutions that engineers in distant offices miss. Sometimes, the manual is wrong not because it's poorly written, but because it was written for conditions that don't exist in the real world. And sometimes, the most important innovations come not from boardrooms or design labs, but from a hangar floor at 2 a.m., where a mechanic with grease under his fingernails looks at a broken system and asks, "How can I make this work when everything goes wrong?" The B-17 Flying Fortress became a legend of American air power, a symbol of technological might and industrial capacity.
But its transformation from a fatally flawed design to a true survivor wasn't accomplished in Seattle or Washington. It was accomplished in English hangars by mechanics who broke the rules because following them would have meant watching more crews die. The forbidden trick became standard practice. The Maverick became a template. And Paul Zuk, who never wanted recognition, who just wanted to bring crews home, proved something that every engineer and administrator should remember. Innovation doesn't always wear a suit and tie. Sometimes it wears coveralls and carries a wrench. And sometimes saving lives requires the courage to say, the manual is wrong, and I'm going to fix it anyway.